Professor from Stanford, Philip? Oh, you're up there already. Okay. Okay, so I present here the panel. Now, after listening to the great talks this morning and this afternoon, maybe we should have had some more representation from the large-scale servers and so forth. So I asked for those people, even though you might not be up front, you're also invited to answer questions and also to ask questions. So the way it's going to be structured is I proposed some provocative questions, which we'll throw out to the panel, and we'll give them a chance to answer the question or to pass, whatever they like. And these are just my questions, so if you have a suitably provocative, non-detailed, high-level meta question, then let's bring it up. The way to think about it is that if you're some big manager, like you're in charge of the whole organization, and you have to make a big decision, you would like to maybe know what to do, and you have some experts up here who might be able to tell you this. So the first meta question is the following. We learned yesterday morning from Bruce, who's up on the panel, Bruce Nordman, that sleep mode is really the low-hanging watermelon of energy efficiency in electronic systems. And while it's great to know, that makes a big difference. However, it's more standards-based rather than technology-based. And so from that viewpoint, is there any point to have high-tech research, that, new types of devices, et cetera? Is there any point to that once every system already has sleep mode? And so to kick that off, let me ask Bruce to answer that question first.
Yeah, I'm still trying to wrap myself around these trees with watermelons on them. But anyways, I understand the point of...
Press button.
Okay.
Is it red?
Not yet. Yeah, the point being, I think the biggest near-term savings is in the power management of devices, and I wouldn't say it's not a technology problem. It's a software as opposed to a hardware issue, I would say, fundamentally, as to how to enable that. I don't think that undermines the importance and value of everything else that was discussed. It's just that we need to have additional people coming in to tackle the problems.
Well, I'm not going to let you get off with easy answers. So here's what I understand, is that you told us it was sort of approaching 10% of total energy use. And I got the impression that sleep mode would whack that down by a factor 10.
No.
Now we're back to 1%.
No, like for PCs, I want to cut it in half with use of sleep,
okay. Not
a factor of 10.
Okay, so you're only promising a 50% improvement. Therefore, there's still lots of room for new technology.
Yes.
Is that what you're saying?
Yes.
Okay. Well, let's get other panelists see what they say.
Well, does this work?
It should work, but they don't.
It is live. But anyhow, doesn't matter. Let's have redundancy. Good. So I honestly believe there's still a lot of room to be gotten in terms of how we do actual wake up and standby and sleep modes. There's a lot more innovation to be done in there. Bottom line is very often what you want to have is a device. You want to be able to have it in a virtual comatose state and be able to wake it up quite effectively. And that's not just purely sitting there with a button and push it on there. Very often this requires a system level strategy of how and when and why to wake up a particular device on a regular basis. So I think the idea of having, let's say, very highly sensitive type of devices that are sitting there and monitoring traffic, that's the only thing they do, ultra low power, just basically be aware of what's going on while the rest of the device is in total sleep, would be very effective. We've been doing a lot of work over the years in standby radios that are just sitting there. They're about tens of microwatts. They don't cost you anything, but they observe that there might be something coming their way and wake up the rest of the device. So having those things that are latently there, but it's not sufficient to just have those devices. You have to be able to have a strategy of how do I basically trade off between latency, what are the protocols, how the system level aspects of how we design this type of thing. So there's plenty of stuff to be done. I think there's There's clearly a factor of 10. There's no doubt in my mind about that. And it's a combination of devices and system.
Okay, very good. Pass it down.
Pass the mic here. Pass the mic to the mic. Is this on? Yeah. Senator, I have no recollection of ever having that conversation. No, I'm sorry. I had a flashback for a second. I'm sorry. I wanted to sort of expand a little bit on what Jan said from our investment portfolio. I think, to me, I wonder whether going to absolute sleep is actually quite necessary. Some of the stuff that we've done over the past couple of years, investing in some of the top researchers in the leveraging subthreshold, for instance, people like Anantha Chandrakasan at MIT, Kaushik Roy at Purdue, and there's a number of others, have shown you can actually make a digital standard cell library and do manual designs at below a quarter volt. That's pretty amazing. Of course, it's very slow, so that's essentially nearly zero as far as standby power is concerned. And yet there's enough to do the housekeeping that Jan was talking about. So I think there's a lot of room there if a number of technical approaches, technical challenges are addressed, like how do you distribute power efficiently, very low voltages, on a chip. I mean, that's a research problem. How do you dynamically do the adjustments? There's a number of enabling. How do you deal with the high variability when you're at a very low voltage? Maybe asynchronous techniques start to become a lot more attractive than they used to be, for instance. So I think there are tractable problems that enable the kind of housekeeping functions that Jan said, where you never actually even have to lose cache memory and have near zero standby power.
That's quite interesting. Go ahead.
So it seems to me we have a lot of sleep modes today, and the problem is that we just can't take advantage of them. So what I mean by that is that every way you use a sleep mode is in a reactive way. So the way you use the DIMMs is that you sit there, and if there are no outstanding memory requests, you put them into low power mode. For a processor, you look at the last increment of time, and you say, okay, I wasn't doing that much work, so now I'll dump the frequency or voltage. So it seems to me the real thing we want to do is be proactive. To be proactive, we have to have things at the higher level of the software stack, applications, the compiler, and so forth, tell us what resources are going to be needed over the next period of time, and then we can say, okay, now I understand I need this many cores active, and in fact I can run my just a couple cores for this period of time, then run them again for this period of time, and I can keep the other ones completely turned off. Or I can actually turn disks off because I know I won't need the files for a period of time. Even though it takes me a second or so to turn the disks off, I know I won't need it for a long period of time. So my question is, where's the research into figuring out how we can start at the application level and the compiler level and all the way through the software to actually do this in a reactive mode instead of in a proactive mode instead of in a reactive mode?
Actually, there's been, as far as I know, kind of research going on in that area since last 10 years approximately. I think it's been emerging. There was a thesis in Stanford about 10 years ago from somebody's no faculty member at UCSD, Diana Simunich, which was exactly doing what you're talking about. It's doing estimation, prediction of what's going to happen with loads. And I think actually it's slowly but surely emerging in the actual commercial world. If you now look at some of the more advanced multi-core chip processors, if you think about the Intels and so on and so forth, look very carefully at the chip diagram. And what you will see there in certain areas is called power management units. Things that are basically now sitting there that try to figure out, hey, here's the temperature of the different processing elements, here's workloads, here's information, what should I do with voltages, what should I do with frequencies, and start actually scheduling functionality. Now, I fully agree with you that having this totally separated out from the operating system is not a very clever idea. What you would like to have is the two intermingled with each other, because they actually are trying to do the same thing. They're trying to do resource management. But I think there's gradually but surely people are putting these things on there, and they are emerging. And I think what it might ultimately, and I think it's very important, and when you were phrasing your question, you were always talking about turning things off, which is an interesting mindset. You actually should think about sleep or whatever it is. Now, the mindset should be, when should I turn something on? By default, things should be off. And when you start doing that, you start really kind of consider the problem in a very different way. Because right now we say, by default, everything is on, and we're going to try to figure out if we can turn something off. I think turning something on when needed is a very interesting type of mindset. And it really can change the way, and it changes the way we think about chip design, but also software design.
Yeah, so what you've said is that we need to have the software express its desires and expectations and needs to the rest of the hardware so that those services can be provided that it wants and no more. And what I tend to be very human-centric in all this, and we want exactly the same thing in our physical environment. We need to have our buildings understand the needs and preferences of those people inside it and deliver exactly the services they need and no more. So in fact, what we need at the micro level is exactly the same thing we need at the human scale level, because human beings are best understood in the future as nodes on the network and the same as other devices. And so fundamentally, they have the same problems and needs to get energy efficiency.
Okay, so I don't want to spend too much time on that question, but you didn't get to the answer I was expecting. I was willing to grant you a factor of 10 improvement, and then we heard from John Schalf, the last speaker, is that, oh, a factor of 10, that's nothing. We absolutely need a factor of 1,000 coming up over the next, was it 10 years?
Yeah.
And so, yeah, the sleep mode is very important, but we'll need something beyond that, and maybe that would justify some of the more exotic research on new types of transistors, etc. So that kind of leads to question number 2, which is sort of similar, and that is that let's say we're very successful and we have great improvements in electronic energy efficiency. This will greatly increase the capabilities, and we'll be able to do more things with cybernetics. We'll have more demands. We'll have higher expectations of servers, and maybe we'll be doing language translation, all sorts of strange things coming out of our servers. And so, rather than producing a drop in energy consumption, it'll only encourage more energy consumption. And so that's, I think there has been some study at Lawrence Berkeley Lab, this displacement effect, which could go even past 100%. It could be that you make things a more important part of daily life, you actually end up demanding more energy. And so let me put that out there. And is that necessarily a bad thing?
I'm not expecting we'll shoot over, so the savings will actually go negative. But we certainly, if you have a house that's easier to heat and cool, people will have it be more comfortable. And I think that's okay to sort of share the wealth. So the take-back effect is the usual name for that. If there are any cases where there's this overshoot, I think that'd be a minority, and so I don't think we need to worry about that so much.
Okay, so I think what you just said was that this thing called the take-back effect, that is that you make your system overall more efficient, and people just want more and more of those services. You don't expect it to overshoot, but you never know. It's sort of nonlinear with what people want. I mean, this factor of 1,000, he didn't blink. He just said a factor of 1,000 in 10 years, just like that.
You know,
John never blinks.
As there's more channels on TV, people watch more television, but there are only 24 hours in a day. And people are asleep some of the time, so there are limits on where these things can go.
You know, having been a long-time observer of the industry, very often the question was, we have so much power, will there anyone need any of this stuff? And of course, we've always been surprised that we've always needed more than we originally thought we would possibly consume. So it may not be quite as easy as you're saying. Jan is shaking his head.
No, I think if you look at the raw numbers, we've been doing quite a good job, and it was coming back over and over again over the last 2 days, actually. We've done quite a lot of work on making computation a lot more efficient, and it is a lot more efficient. But the bottom line is, you look at the numbers of data centers, you look at the numbers of all kind of IT services, the electricity consumption has gone up about 10%. That's basically the conclusion that I drew from a number of slides out there, and I think that's going to continue. The more efficient you make it, the demand is going to increase, and I don't think it's going to plateau out, actually, in the next couple of years. There's tremendous opportunities for more computation and to be used, and it will happen. So I think the net effect will be an increase in power.
Yeah,
So we're going to have to work even harder.
Yeah, I tend to agree with that. The humanity, if you have something that turns very expensive, humanity goes toward a cheaper thing. You provide something ever cheaper, they'll just demand more and more of it. It's insatiable if you're giving the stuff away for very little.
I think it's off limits because there's only so many dollars in the world, right? So if it becomes too expensive to actually do it, we just won't do it.
You get a crisis.
Yeah, but the electronics industry with the software, with everything else, it really represents quite a few percent of all of human effort. Well, it could go from a few percent, it could go to 10%, so forth, 15%, but maybe that's more like medical care. That becomes a bigger part of everything.
There was a question out there.
But also, as some of the speakers said, I mean, some things are more efficient to do digitally. So, just because we're increasing how much is used, what we're doing digitally doesn't mean holistically it's less efficient. If we're, doing something else which was energy expensive before, digitally might end up being a net win.
Yeah, so the problem is we always seem to find new uses, much more than we expected.
I wanted to make a really quick comment, and that's, I know we've been heavily focused on servers, and that's actually very important, but in the office that I sit in DARPA, although we work on components, and so our end goal is much more frequently dealing with embedded computing applications for the military rather than servers. And if you're talking about achieving serious power efficiencies, radically new capabilities jump out at the embedded level right away, putting stuff on mobile platforms, making things more autonomous where you don't have a wall plug. It's revolutionary. And it happens, and I agree with the previous speaker, it happens in the embedded space first, and then it goes up the chain into high performance. So let's not forget embedded computing.
I was just going to comment, Bill Herod, who ran the HPCS program, has made embedded actually the centerpiece of the exascale DARPA. Sorry. Yeah, so Bill Herod, who ran part of the, later on the HPCS program, after seeing what came out of that, has made embedded devices actually the centerpiece for the exascale. So exascale really means more efficient embedded devices and not just aiming just for the high end. It's got to work all the way across the scales.
I think that's also a great way to prove something out. Right? It's a smaller playing field that you can actually prove out new concepts first.
Mm-hmm. So it's a great example. The Defense Department still leads in the development of new technology because of their specialized needs and their willingness to pay for it.
Well, are we talking acquisitions or research? I mean, I represent research. Acquisitions is a whole other story. So,
Okay. Let me summarize the answer to question 2, and you can pipe up if you think I didn't summarize this correctly. I think there's a difference of opinion. Some people say the efficiency will sort of self-limit and it'll end up saving energy. And on the other hand, there was a difference of opinion said, no, as you make it more efficient, more energy efficient, you might actually end up using more energy. I don't think we can answer this right at the moment, but I'm willing to hear another opinion. Go ahead.
Well, either way is a good thing because you can do more with less energy.
Right.
So,
And you serve more human needs.
Let me clarify what I meant by self-limiting. It's not that I don't think we'll necessarily be doing less. I think we will do more. It's just if we get to a point where we can't do more without blowing up the energy beyond some limit, we just won't do more. We'll just flatline. But
Yeah.
if you look at most of the scaling trends that we've talked about over the last 2 days, this is exactly what happens, right? We come up some curve and we flatline at, let's say, 100 watts for a processor. We figure out, oh, this is new technology. We go back and then we run that into the ground and hit 100 watts again, and then we have a symposium and something else.
Yeah, but there is a quantitative way of declaring winners and losers in this argument, and that is if we have this meeting again in 10 years, and instead of it being, and we've increased the efficiency undoubtedly, and instead of it being 10% of all energy consumption, it's now grown to 13% of all energy consumption, then it said it stimulated new needs that we didn't have before.
One thing that I've noticed over time is there's a lot of things that are actually remarkably stable. Like people looked at commute times between countries and over many decades of time, and I think on average they're about 20 minutes usually for society. And people go different distances depending on their mode of transportation, but those kinds of things are relatively constant. If you go back 15 years, a desktop PC used about as much power as it uses today, even despite all this. It hasn't gone dramatically up or down. And my guess is that as we get to smaller devices, more mobile ones, we'll have more of them. and we'll have, our file servers at home, managing our digital portfolios. So our total compute budget will probably be very similar in power 10, 20, 30, 40 years in the future is my guess, even though the distribution amongst the types of devices and their modes will be radically different.
Well, I wanted to make a comment on something that was actually given in the last talk before, which has to do with the question of how much computing do you actually need. So for instance, if you think of climate models are often driven, or the expense in computing that you have is driven by the sparsity of data that you have. So you need to come up with very complicated models on how, for instance, if you have a resolution of 10 kilometers or 100 kilometers, what happens on a subpixel scale, on a very small subpixel scale. And if you can resolve that by putting in, for instance, more sensors into space or more sensors on the ground, that often can have the added effect of giving you better data from which to then come to models. The second thing I wanted to ask, actually, the panel, or put out as a statement is, well, at some point, a lot of the bandwidth is now used for video, right? But you could imagine very easily to have a data center that contains every single movie and every TV stream ever recorded, and multiply that 100 times over the continents, and then you can stream it out over very short distances. You don't need to stream it over very large distances, and therefore your computing power, once you have done that, should go down dramatically, or your requirements. Any comments on that?
Yeah, I have one comment. It's based on, we did this before, right? When we designed out codecs, video codecs, we always assumed it would be a broadcast medium, one center, and you broadcast it to a lot of people. Turns out that things like YouTube and all those other things have changed this dramatically. People are generating information everywhere and transmit it to everywhere. So that whole model of basically centralized and then distributing it out actually has failed. Right now we see a very different social type of networking.
I wanted to come back to something Bruce just said, that the total amount of energy that an individual would use for computing would be some kind of more or less approximate invariant. Did I got that about right? You know, we used to make we used to give talks to the device folks not that long ago, you know, where you would show your Moore's law, and then you would show a plot of the total market for, let's say, electronics or for microchips, and it was also going up exponentially, kind of on a Moore's law sort of way, so that the total amount of dollars in the market for electronics was going up exponentially. Now it's kind of, that actually has somewhat flattened out right now, but you drew these lines and it would show that, well, gee, you know, somewhere in the next 20 years, you know, 30 or 40% of the entire world economy would be electronics. Now,
And instead it became medical care.
yeah, instead it became and the
Walmart, too. Don't eliminate Walmart.
electronics has kind of started to saturate out. But the question I wanted to ask, and I guess that several of the panelists could chime in on this, that kind of goes a little bit against what you were showing, a little bit what you were showing in your talk, that total amount of U.S. electricity going into electronics or consumer electronics or IT or data centers, it doesn't really matter that much, really, which one you look at. It has been growing, right? And so the question I wanted to pose is, where does that saturate out? You know, is it, if we get somewhere on the order of 10%, so that sort of says that for every individual, we're spending about 10% of our electricity bill on information processing. Where does that reach some kind of saturation? Can you imagine a world where people spend 50% of their electricity budget on information or on computing? Or is 10% about where it's going to saturate out? You know, there's a certain threshold beyond which people, I think, you know, would level that out.
Well, I can try that. I think it depends upon the value of the future services, and you have to have some imagination on what that's going to be. Yeah, if the value to the person grows, they'll just spend more on it.
Well, you still have to light the lights and heat the house, you know, and run the refrigerator, right? So
IT services will heat the house.
Okay, so I think we've exhausted question number 2. Did not necessarily.
It's exhausting just listening to the question.
I wanted to
Okay, the questions are not that different. You can comment on the next question just as easily. I'd like to keep it moving. Okay, question number 3. Given how difficult it is to introduce any new technology, and yesterday morning, we heard about a lot of very imaginative schemes, new types of solid-state technology. They always sound good, but then the realists kind of know there are many obstacles standing in the way. So is it going to be like gallium arsenide, all these new ideas of steeper transistor responses and essentially a more sensitive transistor? But is that stuff going to be always like the semiconductor of the future, never reaching the present day? So, Philip.
Well, trying to replace something is very difficult and always probably not the right thing to do. In the corporate world, the worst way to advance in your career is to try to replace your boss, right? So you try to create a new department. That's what you do, right? So same thing with devices. You try to replace what's being done today very, very effectively, very efficiently. It's the bad place to get started. You try to do something different. That's how you get started.
I have a quick comment too. And it also depends on how much trouble the incumbent technology is in. And I think we're sort of at an opportunity point here from that point of view, where if the incumbent technology is in severe trouble, people are more likely to tolerate some risk about what to do next. And unfortunately, we seem to be in that situation or rapidly approaching that situation.
So it's a set of things, parts to this question actually. The first one is kind of, let me refer to the argument that Mark Horowitz made yesterday. Right? There's definitely a lot of space still left in terms of removing waste. And I fully agree with that. That's been the case for a long time. We looked at it, and you looked at electronic designs of the 1990s and said, this is amazing, right? How bad they are and how much they waste. However, we've done a lot of work on removing that waste. If you look today at, especially if you look at, let's say, the mobile market, and you look at the process in the mobile market, those things are very efficient. They really have gone to the core of making sure there's virtually nothing wasted whatsoever. So the only thing that's left is improving efficiency. And I think if you look at the devices that are out there today, we see that's going to be limited. The amount of efficiency that's still to be gained by the existing devices is very limited. So bottom line is, if you want to go further, we have to keep on looking at other venues of improving the efficiency of computation. Now, you have to be patient in those things, right? People say, well, gee, no, it's impossible. It's too hard to introduce new technologies and so on and so forth. I remember exactly the same thing when CMOS was introduced. When we went from NMOS to CMOS, people said, oh, no, too many masks. It's impossible. We'll never
It's not as
do
good
this.
as bipolar.
It's not as good as NMOS.
performance,
It's not as
right?
good as NMOS designs at that point in time. It takes time. And the same thing was said about MEMS. MEMS were basically a niche technology, would never make any impact whatsoever. And now you look at the MEMS industry, there's some big, nice volumes out there. And people have been showing that if you take the patience and the time to build the manufacturing process, to improve the yield at some point in time, you get somewhere. The same thing is true with 3D integration. It's still on that on-ramp. It's been gone for 20 years. But slowly but surely right now you see companies that are starting to master it. So it's going to take time to get those devices out. We're not going to have those things in 3 years, 5 years. It's going to be 10 years out before we can see some of those new devices potentially make sense. So patience, but I think it will happen.
Okay, any comments on that from the audience?
So when we talk about doing something new, introducing these new devices into something new, do you think what Jan Ravi yesterday mentioned about all these trillions of sensors, is that where these new devices where you don't have that much pressure for high performance, you want low power, and you want them tiny, right? Would that be a starting point where they test themselves out there and slowly go up the embedded chain into hopefully HPCs or something? I mean, is that the new paradigm?
Yeah, I think you're suggesting one of the paths that might be taken for introducing something really new. And that's a good suggestion.
So I kind of wanted to follow up on both of those things. I think we need to be a little bit careful in terms of what application you're talking about, because for some of the technologies we were discussing, it's probably a few $1 billion-ish to actually get that technology in, and that's maybe even on the low side. And there's only certain applications that could really support that kind of investment. So I guess that's kind of why I was trying to make the pitch yesterday of, I think there's only so many of those that we could really go after, let's say, hardcore computing, because there's just not that many billions of dollars, that are available to be spent on it. So I think we need to, for some things, we need to think carefully about what are the devices that would actually be worth that return on investment. And so I totally agree with you on that, you have to be sort of patient, but at the same time, we need to probably be careful ahead of time so that we don't spend the money we have on a bunch of things that won't really pan out.
Any comment from the panel on that? Any suggested commercialization path?
Yeah, I think it's only until fairly recently that power efficiency has been a major factor. I mean, if I look, Jeff was sitting here a moment ago, I was participating heavily in the device community and watching those trends, and certainly industrially, they were squeezing every last drop of performance, and power was like maybe a tertiary variable to optimize. So that's only very recently become a key parameter to optimize around. So I think there's room to be gained just by starting to think at all levels, using energy instead of performance, which has not been the case.
Go ahead.
Okay, so we're talking about new devices. This led to a kind of a tangential thought, and I would like the panel's opinion on this. So we've been talking about stuff in terms of let's improve computing, and power will always be this somewhat expensive bottleneck resource. So my question is the work that we are doing here, could it have perhaps an impact on making energy cheaper, more abundant, perhaps a new grid, better ways of building renewable resources, and I don't know, cold fusion, sci-fi stuff. So that while computing is inherently at the same level of efficiency, energy just got a whole bunch cheaper, kind of like how internet bandwidth got a whole bunch cheaper. Any thoughts on that?
Well, I have an answer to that, and that is that bits have always been cheaper than joules. And so we can make big improvements in bits, but if you're talking about big things, big hydroelectric dams and so forth, those things, it's much harder to have orders of magnitude improvement in that.
But fiber optics all of a sudden make bits over the network, a whole bunch cheaper. We never optimize.
Well, that you're proving my point, is that in the information technology industry, we can talk about making many orders of magnitude improvement. But if you're selling gallons of gas, for your information, a gallon of gas is 180 megajoules. That's kind of like very difficult to make big changes in, and that's why we have Department of Energy and LBO and other things. So we're lucky in the electronics industry. We can talk about making big changes, but in energy, changes take place over a 100-year time frame. And we don't really change the amount by orders of magnitude at all. We just maybe sometimes transform. We're looking forward perhaps to changing over, when they changed from coal to petroleum, that took 100 years. Now we're probably going to change from petroleum to things that are more solar-based. We're in the middle of about a 100-year transition there as well. I'm answering your question because I used to work at Exxon, so I got a feel for the pace of the energy industry, and everything is in slow motion compared to what we're accustomed to in the electronics industry. Change happens, but it's sort of like a glacier moving. You can hardly tell anything's changing at all.
So in other words, the abundance of computing power, in your answer, the abundance of computing power, orders of magnitude changes in our fields will have absolutely no impact on energy.
We'll use more. I think.
Will have no impact on the abundance of
The abundance, no, you have oil exploration. They use a lot of high-tech gear to do the acoustic imaging under the ground. That has become very, very, very advanced. Nevertheless, if you speak to an oil person, what is it, you ask them, what is the most important resource for discovering oil? He says, show me a piece of land where nobody has drilled before. Okay, and that's the biggest resource. Okay, so I think we have to move on. We're sort of getting toward the end.
So the last 2 days, there's been lots of devices and techniques that have been spoken about in terms of improving efficiency. I'd love to hear from panelists, each of the panelists, maybe what do they think is the most important thing there? Is there a particular device that they think? Is there a particular technique that they think? I'd love to see the variances and answers from the panelists. Thanks.
Yeah. So the question is, what, as far as you can tell, what is the most important thing to be done? And Jan, you're never at a loss for words. What is the most important thing? You only get to pick one.
I have only one. I think the most important thing you can do is really think about energy from a top-down fashion and purely systematic fashion. More than anything you can do at the device level, at the component level, is really think about what's my application and what's the most effective way of doing it. System level perspective, absolutely.
Yeah, I think we would say, I think you got to look at the holistic problem, all the way from the chip, all the way to the environment, and try to integrate all those components to make it a very efficient system. So rather than very focused on individual components, which a lot of our developers tend to do, we try to look at the whole system now and look at where we can gain efficiency across everything.
As we're trying to reduce energy use, we're trying to make better use of that energy physical resource. And since electronics are really about information, what we fundamentally need to do is make better use of the information that we already have. And I just like to offer two examples of that. Set-top boxes in the U.S. use more energy than servers do. They're scattered about, over 100 million buildings. They're not concentrated like data centers are. The companies that spec those don't pay the power bill, so they don't have the information to do it. We could rearrange the regulatory scheme so that the service provider pays for the electricity. They specify the hardware, they specify the software, and they have an ongoing financial relationship with the customer and a network connection to the device, so they could simply, pull the device once a month, subtract from the bill, and then suddenly we've solved that information problem. The information exists, we're just not using it. Another example is that we have lots of every building around here has a network inside of it. But I don't know of any around here, there's probably a few, but it's very rare that the information in the our wireless networks or in the internet contributes to understanding how the building should operate in terms of what people actually want. And again, we're just not making good use of the information that we already have.
Well, again, a holistic approach of approaching this, solving this optimization, basically it's a huge optimization problem. It's solving from devices to circuits to systems and so on. A holistic approach is really important. In the past, there is a lot of fat in between compartments. There's a department to do device engineering, there's a department to do circuit design, there's another department to do software design and so on. And between each department, between each compartments, there's a lot of sandbagging and buffering to make sure that things work in the middle. But these days, these kind of buffer cannot exist anymore because these are the waste that we all talk about.
So just to briefly, I kind of agree with what a lot of the panelists said, which is we really haven't been optimizing until fairly recently. At least I can see that in the device world, and I'm sure that's true in circuits and as you go up the chain. We haven't really been using power efficiency as your first optimization variable. I know when I was learning how to do device engineering, it was driven home to us, look, drive current is the most important thing. Put that stake down and then optimize everything else after that. And I think that's true also at the circuit level and at other levels. And it's a new paradigm. We have to think now with power efficiency as the first stake in the ground and then optimizing everything else around that. And I think that's only starting.
But how objectively can you holistically optimize? At the end, you have a bunch of people that will try to blame each other for anything.
Well, that's true. You still, to do any complex problem, you have to break it up. And there'll still be device people and circuit people and systems people. But to get them to say, all right, even within their own compartment, to say, I'm going to use power efficiency in how I spec what I bid. I'm going to use power efficiency in how I design a device and how I come up with a circuit block, something like that. I think a lot of progress can happen from that switch to that viewpoint.
Okay, so I was looking at my question number 4, and it's really pretty similar to question number 3. It points out some of the challenges of variability, reproducibility, threshold control. This is pretty much the same as all the obstacles we talked about in question number 3. So I'm going to withdraw question number 4 and say that we've discussed that. And I'd like to, since we're keeping it here kind of late, so let's throw it open to the audience. Any burning questions from the audience that you would like to address to the panel?
It's been hit on a little bit through the questions here, but the question of what are the critical needs that will drive the disruptive technologies that will adopt the new chip designs that we were talking about the first day. So we've said we just wait. You know, I'm saying we just wait, and eventually it will be adopted just like CMOS. But it might be helpful if we can think about what are those needs, things that we can't do today, we'll never be able to do with silicon, that will eventually drive the adoption of the new technologies.
Anyone want to take that?
Well, I guess there are two major kind of categories of things that we talk about over the past 2 days. One is really high performance computing and large scale computing, and the other is really low power, distributed personal electronics, embedded everything. So there are two kind of, if you take a very broad stroke, this broad brush in here, there are the only two things that we talk about. And for those new devices, new technology, it seems to me that the really low power, extremely low power, almost zero power computation is the one that has probably the largest opportunity for growth.
And that would include sensor networks.
Absolutely.
I can use some example from some of the DARPA interest and the military interest, and that's, we like to think often when we do new programs, our management says, okay, don't talk to me about technology. We're technology agnostic. Talk to me about a capability that we don't have today, and how do we get there? Some concrete examples: autonomous operation of either ground vehicles, you remember the urban challenge, right? Things like this. Well, there were some of those, I was lucky enough to be there, some of those vehicles were stacked with servers with giant cooling air conditionings on them. I don't know if you saw some of them. It was really, really embarrassing a little bit. So capabilities, if you could do that without having an SUV stuffed full of air conditioning, to be autonomous, to autonomously navigate. Same thing for air vehicles, to put real autonomous. Right now they're controlled from the ground. What would it take to make them totally autonomous? That's a revolutionary capability that motivates investments like this. And that's technology agnostic.
And you would add even energy harvesting on top of that.
Yeah,
Absolutely. It wasn't battery powered, but
Absolutely.
be powered by the environment.
Sounds like a new DARPA job.
I don't think it's a job. I think it's a solved problem for us.
Excuse me?
Solvable problem.
Harvesting?
No, the autonomy.
Well.
Yeah, but I can say from experience
Depends on the size you look at.
that at the urban challenge though, that it took a rack of server, blade servers with a giant air conditioner to just barely navigate the course.
But I like to make since we're talking automobile, when I was at AFRL, we looked a lot into automobiles. And being in Dayton, which is kind of in the automobile industry, there were lots of people who were talking about that. And so once I talked with some of the GM folks, and they said, well, in 1990, the value of a car, the electronics in a car, was about 5 to 10% of the car. In 2004, it was about 50%. In 2010, it's about 75% of the value of the electronics or of the car is in the electronics. And what they have been observing is that many of these things, like for instance, nowadays you have automatic braking if you get too close to the car, you have lane shift, you have so many of the capabilities that are slowly being built and adopted and accepted by the people, which 5 years ago or 10 years ago, nobody would have said, well, I don't want to have something that has a predictive braking for me. We don't want that. So I don't think it's only, what I want to say is it's not only a technology challenge, but it's also a social problem.
Okay, so I think your question was a very good question, was very well answered. I like Philip's answer a lot, is that we'll find the critical path for the introduction of new technology at the low end, at things that are very small and consume very low power, and also at the very high end when we have extremely giant servers.
Actually, I think that's the problem with redundancy. You have to choose. So actually, I tend to disagree with Philip about the high-end part. I fully agree with the low-end part, but I believe that the majority of the new innovations will come from the high-end side, from the low-end side, as they have done in the past. Think about it. 1992 was when the first paper was published on concurrency to reduce energy operation. That was the first time. At that point in time, it was used for some obscure signal processing applications, very dedicated, and show you can actually improve. Slowly, at that point in time, you went to Intel and they say, yeah, it's a great idea, but it doesn't apply to laptops or anything like that. It doesn't apply to desktops. We have plenty of power. And they've seen over the time, it has permeated through the mobiles, to the desktops, from the desktops to the large-scale centers. I think that the idea is, hey, simple is good, lots is good, things like that. And I believe the same thing will happen, is that a bunch of these ideas that basically are emerging from the distributed world and how to basically improve efficiency to the maximum end will probably permeate to and will potentially influence what's going to happen in the high-performance computing world.
The really interesting things in electronics, I guess, are at the very low end and the very high end, you know, what I call power deserts or power oceans. But the vast majority of energy in electronics is used by the boring stuff in the middle. And so I just really want to plead with people at Berkeley campus and elsewhere to reserve some portion of your intellectual collective budget for the boring stuff in the middle, which uses most of the energy, because we do need to reduce that, and we do need really smart people working on some of these problems. So you know, it's not going to be a majority of the effort. You know, I don't expect it to be proportional to, you know, carbon emissions, but probably maybe a little bit more than is given right now.
Okay, well, I think everybody needs to be congratulated for staying to the very end. So I suggest you give yourselves a big round of applause.